All right, subscribers, welcome back to another episode of Science with Surback. Today, what we're going to be talking about is section 5.1 and 5.2, which introduces us to AP Chemistry Thermochemistry unit. And so before we get going into these notes, I want to outline a couple of objectives. Objective number 1, give examples of different forms of energy. Objective number 2, list the important units in which energy is expressed and convert from one to another. Objective 3, define the first law of thermodynamics both verbally and by means of an equation. Objective number 4, describe how the change in internal energy of a system is related to the exchanges of heat and work between the system and its surroundings. And objective number 5, define the term state function and describe its importance in thermochemistry. All right, so the other thing I want to point out is that your note should have blanks, and these blanks are correlated to these highlighted words or equations. So we start out here with thermodynamics, and thermodynamics is simply defined as the study of energy and its transformations. So it's a comprehensive view of what is happening in a particular system. Now, for us in a chemistry class, we're concerned about the thermochemistry side of things, which is defined as the study of the relationships between chemical reactions and energy changes involving heat. And so what this really means for us is during a chemical reaction, we are interested in the heat change, which allows us to find the energy change of a chemical reactions. So I'll pause and I'll write that down. So again, in chemistry, we find the heat change, which is really easy to study or find in the lab, and then we correlate that to the energy change in a chemical reaction. Now, as we get underway here, I want to introduce a couple of new terms that are associated with thermochemistry. So the first thing that we have here, we have four main terms that we'll use throughout this process, throughout this unit on thermochemistry. And so we first get to energy, which is defined as the capacity to do work or transfer heat. A pretty broad definition, and so what we need to do is we need to hone that in and separate it out into its two components of work and heat. Now, work, you can see, is defined as the energy used to cause an object with mass to move. So this right here, if we go back to physics class, has an equation, and that is work equals force times distance. So how much force is that object having, and how far is it going, or what is its distance that it's traveling, can help establish our work. Now, heat is defined as the energy used to cause the temperature of an object to increase. Okay, so heat, we're looking at the temperature change, which again is a very measurable quantity that we can do in chemistry. And then force is defined as any kind of push or pull exerted on an object. A great example of that is gravity. Now, I want to add that note here about heat, which we have this. Heat is a very easily or a very measurable quantity we can have in chemistry. Now, all four of these terms can be applied mathematically and conceptually to explain what is happening in a chemical reaction. Okay, so what we're going to do now, we're going to take some time to explain many of these terms here. We're going to go and talk about energy, work, and heat. Force, we don't really use a whole lot in this class. We just have that there because it does get tossed in there with some thermochemistry items. So the first thing that we'll start to do, or the first thing that we'll start to think about here, is energy. And we can separate energy into two categories. The first category is kinetic energy. Now, kinetic energy is just the energy of motion, and it has this particular formula where the kinetic energy equals half times m times v squared. Now, what happens here is that as the quantities of mass and velocity go up, or they get bigger, you're going to have greater and greater kinetic energy. And now for us, again, think where we are in chemistry. We start out here with the atom, and all atoms are going to have mass and they're going to be in motion. So we have two things that can be directly applied to our kinetic energy formula. And I am going to write this down. Atoms having mass allow that m quantity to be fulfilled in our kinetic energy formula. And just so everybody knows here, I'm going to abbreviate kinetic energy as Ke. And so we get down here, atoms having motion. Remember, they just don't have motion when they get down to absolute zero, which is something that we haven't even fully reached, and it's something we really don't talk about a whole lot in this class. So this motion part is the v, or velocity, in our kinetic energy formula. Now let's talk about our other type of energy in potential energy. So potential energy is just defined as the energy an object possesses by virtue of its position or composition. And so what it's looking at here is really the stored energy that some component, some device, some chemical has in relation to other objects. Now, for us in chemistry, and we'll see here just in a second, we are wondering, okay, well, if we have two chemicals and we put them together, what could they do, and what energy would either be released or required for that reaction to happen? So let's put us into two different examples. Let's say we have a ball at the top of the hill and it begins to roll down. So number one, the potential energy is greatest when the ball is at the top of the hill. And again, I'm going to abbreviate potential energy as PE. And our kinetic energy is greatest when the ball is at the very bottom of the hill. Now, one thing that we need to keep in mind here, one important concept here with our energy and this ball rolling down the hill, is that as the ball rolls down the hill, potential energy is converted into kinetic energy. And now in our second example, let's take this to the chemistry side of the house here, and let's talk about this. Let's talk about baking soda and vinegar, or acetic acid and sodium bicarbonate being mixed together. Okay, so here we've all seen this reaction where we mix vinegar and baking soda together here, and we mix this together. But before we mix it together, the potential energy is greatest when the two reactants are separated into their individual beakers. And kinetic energy is going to begin to occur when we mix these two reactants together. Now, our potential energy is converted to kinetic energy as the reaction occurs. Okay, so let's talk more specifically, well, how can a chemical, or how can an atom have potential energy? So let's go ahead, let's look at this next page of notes. In this, we have a potential energy here called electrostatic energy. Now remember, atoms are composed of protons, neutrons, and electrons. And as those different charges interact with one another, they produce this electrostatic energy, which is a form of potential energy. Now, you can see this fancy formula. We're not going to use this in this class, but this does describe the electropotential energy, again, a form of potential energy, in a particular atom. Now, a couple of things here. This right here is the electrostatic energy, and these two things right here, Q1 and Q2, are your charges that you're looking at interacting. So whether you're looking at interacting two different electrons, you're looking at interacting that electron and proton, we can get that electrostatic energy in atoms or really any charged particles. Now I want to stop and I take a little bit broader terms here, and I want us to have a goal in mind for thermochemistry. So the goal of thermochemistry is to relate the changes in the macroscopic world, the one that we can visually see, to the kinetic or potential energy a substance have at a molecular level. Now, keep in mind this point here, that when substances react, they release chemical energy of their potential energy that is stored in the arrangement of their atoms. Okay, so we've introduced a lot of things about thermodynamics. These points right here really outline, okay, what are we after? What's our objective in chemistry for this heat of reaction or this thermochemical process? So let's go ahead, let's get a little bit more in depth. We're still going to be talking about energy, but we're going to move on to our units of energy. Okay, so our units of energy, we're going to use mainly the joule and calorie as our base unit. We'll also use some kilojoules and some kilocalories a little bit later on. Okay, so 1 joule is defined as 1 kilogram squared meter per second squared, and it is the SI unit for energy. Now, oftentimes things have, or objects or chemical systems release or need lots of energy. So we're going to have really big joule numbers, and so they express it as a kilojoule. Just remember that base 10 system is to go from a joule to a kilojoule. There is 1,000 joules per 1 kilojoule. Okay, so something to keep in mind as you go through this process. Another thing is our calorie. Now, we'll talk more in depth about a calorie and calories we see on the back of packages and labels for food. But in chemistry, a calorie is defined as the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. So 1 calorie, and I want to point something out here. This is a little c, okay? Little c, or lowercase c, all right, is equal to 4.186 joules. So we can convert between joules and calories if we need so. And now we get down to the nutritional calorie. The nutritional calorie, I want to point out this. This is an uppercase or a capitalized C. Okay? That is very important to distinguish, because 1 uppercase calorie, nutritional calorie, is equal to 1,000 calories, or we call that 1 kcal here for our units. Okay, so very important here. I know I didn't go over a whole lot, but this is a very good reference sheet to do while you are looking at problems and going through that process there. All right, so let's get a little bit more into detail about our thermochemistry, and we'll move on here to a new topic. And that new topic here is our systems and surroundings. So the system is defined as the part of the universe that we are interested in studying. So it's a very detailed particular spot. And so us in chemistry, we are going to be looking at the reactants and products. that is our system. It's a very defined, it's a very small part of the universe. Now, the surroundings are defined as the rest of the entire universe that is not the system. And I have a couple of different systems I want to talk about. I didn't have you write any of these things down, but I will highlight these here as we go through them. So the first one here is an open system. And it's defined as a system in which matter and energy can be exchanged with the surroundings. So I have here an uncovered pot of boiling water. If you can think of a coffee cup with no lid is another great example of an open system. And so we move down here to a closed system. And again, I would underline these because these are important terms. But it's defined as a system that can exchange energy but not matter with their surroundings. So we have here a coffee cup calorimeter. And essentially what the difference is between an open coffee cup and a coffee cup calorimeter is this. There is a lid and a two-layer cups, or a lid and two layers of cups. That's what I should say there. Okay, so that's the big difference there. And then we get to an isolated system. And we don't often see this, but an isolated system here is defined as a system in which neither energy nor matter can be exchanged with the surroundings. So think of like a sealed container, what we have known as a bomb calorimeter. So this would be, again, a sealed container. Okay, so again, I didn't have you write a whole lot of these things down, but these are important things to know. These are important definitions to know as well. So just have that in mind as we go through this particular unit. Okay, so now what we're going to do, we're going to look at some things that we can actually study here in chemistry, okay? So we are going to talk about the transfer of energy. And usually we have to talk about the transfer of energy because it's oftentimes very difficult to express or identify or even locate the amount of energy in a system. So energy, remember, is the capacity to do work or transfer heat. So work, remember, is the ability to move an object here. So some object's going to have some force. You're going to move it some distance. Whereas heat is the energy. Heat is the energy of transferring heat from hotter objects to a colder object. So a great way to see work and heat is through some examples. So an example here for work is lifting a box. In this case, the box here has work done on it because it increases the potential energy of the system. And then for heat, a real simple example here is boiling water. And so what happens here with boiling water is that heat is released, or a release of energy causes the temperature of the system to increase, and then heat is transferred from the hotter system to the cooler surroundings. Okay, so that brings us here to the first law of thermodynamics. Now, there are three laws of thermodynamics that we'll look at here. And so the first law states that energy cannot be created or destroyed. And it's known as the law of conservation of energy. Now, we need to be aware of a few things here, and we're going to call internal energy the total energy of the system. And we abbreviate with that with a symbol E. Now, it is the sum of all kinetic and potential energies of all components in the system. And very importantly here, we have a very simple formula of our internal energy, which we call delta E, or the change of internal energy, is equal to the final energy minus the initial energy. Now, it's very important here that we note this, that the energy transferred from a system must be transferred to the surroundings and vice versa. Now, another key thing here is this, final minus initial. If you can remember final minus initial for thermochemistry, a lot of the mathematical functions here are going to be pretty straightforward, but we have to keep in mind final minus initial. Again, final minus initial, this will pop up several times throughout our thermochemical unit, but it's a very key thing. Now what we can do, we can take a little bit closer look into our internal energy formula. So what we have here is this. Obviously the internal energy formula is written here, and it says yes, it's going to have a number, and it's going to have a unit, usually in the form of joules. Sometimes you'll see it in calories, but it's going to have some unit associated with that. And then here is really important here, our values for being positive or negative. So a positive delta E, or change in E, and I should note that here, a sign, this is for delta E. And so what that means is that your final energy was greater than your initial energy. Now, a great example here, if I take number 1 here and I continue our example, a great example of this would be water breaking into individual components. So if water would break down into hydrogen gas and oxygen, O2 gas, okay? The delta E in this case is greater than 0, okay? So what that means is that there is a gain of energy by the system. Now, if we have a negative for work and heat transferred to the surroundings, the final energy would be less than the initial energy. And so if we draw another arrow here, an example here is just the reverse process. If we have hydrogen gas and oxygen gas be combined together, they would be combined together to form H2O. And this process right here would actually release energy, or has a delta E less than 0. So some important things as we think about here internal energy. Now let's get a little bit more specific into the units. And I'm not going to add anything extra, but I am going to take the time to go over some of these units. Okay, so we have our delta E formula. Just before we said, hey, we could say, hey, this is the final, this is the initial energy, but we really didn't get into, okay, how can we incorporate both heat and work? Well, here's how we can do it. The change of internal energy is equal to Q, which is our heat, plus our W, which is work. So now we have a formula to deal with as we have heat and work and its relation to energy. And so a couple of things to remember. If or when we have a positive delta E, there's a net gain of energy by the system. Now, a negative delta E would mean we have a net loss by the system. A positive Q means that heat was gained by the system. A negative Q means the system lost heat. Now W, if we have a positive W, that means work is done on the system, and a negative W means work is done by the system. Now, it's really important in thermochemistry is to remember signs. So I've outlined this table, this chart for you. It is very important to understand and recognize, okay, if I have a positive Q, what does that mean? If I have a negative W, what does that mean? And so on and so forth. So signs do make a difference. And so I am going to write that down here. Signs are important to thermochemistry properties. Okay, so let's go ahead. Let's put this formula to the test, all right? Okay, so in this example, it says gases A and gases B are confined in a cylinder and piston arrangement and react to form a solid product C via the reaction scene. And as the reaction occurs, the system loses a 1,150 joules of heat to the surroundings, and then the piston moves downward as the gases react to form a solid, and as the volume of the gas decreases under the constant pressure of the atmosphere, the surroundings does 480 joules of work on the system. We want to know what is the change of internal energy in the system. So we start out here and we identify the formula that we've just been talking about, delta E equals Q plus W, and we just list out our variables. So delta E, Q, and W, okay? So what we have here is delta E is going to be our change in our internal energy. Now that's the question that's being asked, so this will be our question mark. Now our Q is related to heat, and I want to highlight this. It says the system loses 1,150 joules of heat. So because it loses, the sign of Q is 1,150, and that is negative, okay? So we have negative 1,150. Now, the surroundings do 480 joules of work on the system, okay? So because they do 480 joules of work, that is a positive 480 joules. So the other thing that we need to double check here is we need to make sure both our Q and our W need to be in the same unit. They're both in joules, but if they weren't, you need to convert it so that they are both in that same unit. And so all we need to do from here is we need to plug this in. So delta E equals negative 1,150 joules plus 480 joules, okay? So all we need to do in our calculator is put that in. So we're going to take negative 1,150 plus 480. We press enter, and we get a value of negative 670. And again, our units need to be included in here, so negative 670 joules is our change in internal energy. And that's how we would utilize that particular formula. All right, so we're getting close to the end here. We're going to change gears just a little bit and talk about endo versus exothermic reactions. All right, so an endothermic reaction is defined as the process that absorbs heat from the surroundings. The best example here is melting ice. So as ice is melted, heat passes from our body to the ice cube. And an exothermic process is defined as a process here that transfers heat to the surroundings. So heat flows out of the system into the surroundings. And I have an example here, combustion of gasoline. If you've ever put your hand over your car's hood after it's been running for a few minutes or several hours, you'll feel that heat from that combustion reaction between the gasoline and your engine. Now, I want to go a little bit further here in the melting of ice, and I want to ask you this. Why does an ice cube feel cold when touched? And the reason that an ice cube feels cold when touched is because heat is being transferred from our body to our ice cube to allow it to melt. So because when we touch that ice cube, it feels cold because heat is leaving our body. Now, I want to end our section 2 here talking about a state function. So a state function is defined as a property of a system that depends only on the initial and final states of the system. It does not depend on the path the system took to get there. And so all it cares about is what happened initially, what happened at the end, and tell me the results. I don't care how you got there. And so for us, a thermodynamic or a thermochemical state function is our equation for internal energy. However, our Q and W is not a state function. And so the best way to think about a state function is through another couple examples. And so our first example here is a battery example. And so a battery can power a flashlight by producing heat and light. And that same battery can also power a toy car, and that toy car produces heat and work. Now, in both cases, whether it is powering this toy car or it is powering that flashlight, in both cases, the change in internal energy of the battery is the same. Now, let's do another example here, and this is the altitude difference between Chicago, Illinois, and Denver, Colorado. Okay, so here is the state function here. No matter if you fly or if you drive, the altitude difference is still going to be the same with a difference of 4,684 feet. All right, so we've done a lot. We've introduced a lot about thermochemistry. Hopefully you're starting to absorb some of those terms, and keep in mind that we'll utilize that throughout our thermochemistry unit. I hope you have enjoyed this episode, and like always, if you haven't already, make sure you subscribe.